So this talk was really born of just interest, right? So if any of you had similar experience to me, you first saw the Fundamental Theorems of Calculus in high school, and your high school teacher did not really take the time to either A, prove them, or B, even like give you a kind of intuition for them, right? For where they come from. We learn them, we start using them, and then I think we take them for granted pretty quickly. So I wanted to learn more about them, how they related to one another, and answer some of these questions. And I found it interesting, so I thought maybe at least one of you might find it interesting. So let's talk about it. So if you don't do calculus a lot, there's really two ideas you have to get through to kind of understand the fundamental theorems of calculus. Those are and these are kind of the big ones, right? It's the derivative and the definite integral. So I'll just intuitively kind of talk about what these are before we talk about the fundamental theorems of calculus. So let's start with the derivative, right? So we have a function, and I should say at the outset, I'm going to assume every function I'm talking about today is continuous. Some of these theorems will hold if the function's not continuous, but let's just, make it easy on ourselves and assume everything's continuous. X squared definitely continuous. So what's the idea with the derivative? Well, we're given a function. Hopefully it's smooth, differentiable. And we want to find the rate of change of this function at any point. Geometrically, we can think about that as the slope of the tangent line to the function at any point. So instantaneous rate of change. These problems are inspired from physics, right? So say this represents a particle, its position in space, right? So we want to find out its velocity. That would be its derivative, right? But just algebraically, we don't need to know how for now. But if f of x is x squared, its derivative, which I'll be noting at the time of x, is 2x, right? So, yeah, thank you. Two is not right. So that looks like a line, right? So what's the relationship between these two functions, right? Here's my initial function, and this one should tell me the rate of change of the white at any point. So how does this work? At -1, this function is decreasing. How quickly? Well, that here, right? The slope of this tangent is -2. So I won't say any more on the derivative, but as I talk about today, just think slope of the tangent line, or think instantaneous rate of change. So the other idea is the definite integral, which, as far as I'm going to take it right now, is a very, very simple thing. So for our purposes, all this really means is the area under this function, technically the signed area, but we're not really going to be worried about that today, from A to B. So if this is my function f of x, here's my A, here's my B. This notation represents this area, right? And that's all we need to be able to understand, I think, for now, right? Derivatives, slope of tangent lines, integrals, area under curve, and we're off. So can somebody give me, you don't need to say all the symbology, but like the essence or whatever you think of for the first fundamental theorem of calculus? Or the statement, right? Not all at once. Nobody? Okay. I don't know how many math PhDs we have in the room, but here is the formal statement of the first fundamental theorem of calculus. Okay, I'll talk about it more in a second, but first, let me get the second. So, might be problematic. What's this capital F? Well, it's what we're going to call the antiderivative of little f. So maybe this requires a little bit of explaining, right? We call this the antiderivative of f because when we take its derivative, we get f. So the Rate of change of this function is our original function, right? So there's a couple funny things going on here. First of all, this theorem is incredible, I think, because we're talking about the area under the curve from A to B, right? That's what the left-hand side is saying. And somehow, all of the information about the area under that curve is distilled into simply 2 points. So we're looking at an interval that has infinitely many points, but it turns out if we have this function f, we only need to know it at 2 points to be able to evaluate that area. So that's kind of surprising, right? But then also this, right? This, I think, is the big mystery of the definite integral, if you don't take a lot of time to study it, is why does differentiation relate to integration? Why is it that rates of change and area under the curve are somehow intimately related to one another? It's not immediately clear. At least it wasn't for me when I first saw these theorems, right? I think in a math class, the way it goes is a lot of times you spend the semester learning about the derivative, how to take derivatives, all this stuff. And then kind of out of the blue, we say, okay, we're going to start learning how to do antiderivative. And you introduce the definite integral, and then that goes into the indefinite integral, and at some point we lose the connection. It's like, okay, but why did we start looking at the antiderivative in the first place, right? So we're going to try to unravel that mystery a little bit today. And the first step in unraveling that is right here, first fundamental theorem. So the first kind of connection between the derivative and integrals we see right here. This statement is saying if I have an accumulation function, meaning this function tells me the area from A up to x for any x, so that's my input variable. When I take the derivative with respect to x, I just get my function back. So it means that integration and differentiation in the sense are inverses of one another as operators, right? And this first formal statement of this was given in 1666 by Isaac Barrow, actually. And this idea that these are inverses was understood heuristically even before this. And I'll give you kind of an intuition for this in a moment before we prove it rigorously. But this is the exact year, 65, 66, that Newton first developed his calculus, right? But he didn't really publish anything for a while. And then Leibniz made his using a much better notation. The notation we use today, he introduced this symbol. So that's right. And so that's why the conflict comes from. But actually, Isaac Barrow is the first one to state this formula. And he was a mathematician at Cambridge. But this idea was understood geometrically in the following way. Maybe I'll put this up here for a second longer. Nah, I won't. So what's going on here? Well, we're starting with an accumulation function. That's a big word, but it's not so scary, really. I'm going to call it A of x. A of x just means the area under my curve from A up to x, where A is some fixed number. And I use t here as a dummy variable to not have an abusive notation. We don't want x and x is like what is which. This just is saying t runs between these values. Like we just essentially summing up on that interval, right? So up to some x. Okay. So there's my area. So when you teach Business Calc 2 here, we have to draw what accumulation functions look like. And I tell my students, I'm like, if the function is moving further away from the x-axis, my accumulation function is increasing what? More faster or slower? Anybody? Faster, right? Why is that? Well, we're further away from the x-axis, we're accumulating area more quickly, right? That is really what this is saying. Kind of heuristically, right? Where the rate at which I'm gaining area, so this is what it's saying, the derivative, the rate at which this is increasing, is directly proportional to the height of my function. And the height of my function at x is just f of x. So we already have an intuition for this, and people understood this before calculus was really formally put together, but that's not good enough for us, right? Let's look at this and try to prove it. So a prime of x is exactly what we are looking for, right? Just written a little bit different. We want to show that this is f of x. And what I'm going to do is I'm going to use the limit definition of the derivative. So some of you might lose me for a second here, but I think I'll gain you back in a second. So what am I doing? Well, adding a little piece here. So this point now is x plus change in x. That width is just change in x, right? But I'm just adding a little more area. Here. So I'm going to write this in terms of the integral. It's the integral from a x plus change of x. Of then to here. So that makes it pretty easy to see what's going on. Right. Oh, my students, if only they were here, then they could yell at me the way I yell at them. Right. Very problematic. What's change of x? Nobody knows. Thank you. So what's happening here? Before I do it algebraically, which would be very easy, let's just think about it geometrically. The area from a to change of x minus the area from a to x. So this whole area up to here minus this area. So really that the numerator is just the area of this region, right? Right. So I'm taking the larger area minus the smaller. I'm left with that sliver, that new sliver, right? And we can do this quite easily algebraically if we understand how integrals work. This just becomes the integral from x to x plus change in x. Hey. Thank you. I got plus 0. From a, no, wait, why a? Should be x. Oh, I see. Okay. I thought we were breaking it up first. No, because I'm just left with this, which is the integral from x to x plus change in x over change in x. And now we're going to get some inspiration from this, right? So this sliver is really close to something else, namely this little rectangle here. But we got this small error, which I'm going to call epsilon change in x, right? So the area in question is just the area of this rectangle plus some error term, right? That's represented by the square area. Could be positive, could be negative, right? But I'm just going to say plus, and the sign could be in there. So somebody, what's the area of the rectangle? Well, what's the formula for area of a rectangle? I'm going to make it as simple as possible.
Base times height.
Thank you. Finally, right, base times height. Base is change in x. Height is f of x. So this is f of x times change in x plus my little obnoxious error term over change in x. These are going to cancel, and there's going to be no more change in x in that term, so I will pull that out of my limit, because it doesn't depend on change of x anymore. And this gives me f of x plus something else. And what am I going to hope about this part? That it goes to 0, right? So I'm going to show that the absolute value goes to 0. Should be sufficient to show that it goes to 0, right? Because I don't know if that's positive or negative. So let's just do this. We know 0 is less than or equal to this. Oh, this notation might be confusing, so I'm gonna. That's a subscript for now. So That area, remember, is this little area. That'd be a little, hand wavy here, but that area is certainly less than the area of that box, right? That rectangle. Because I'm doing absolute value, I'm going to say, actually it doesn't matter. This is less than or equal to the limit as change in x goes to 0, absolute value of the area of that little rectangle over change in x. Well, what's the area of this rectangle? Once again, the base is change in x, but now the height is just that minus this, right? And I have absolute values here. So this is absolute value of change in x, that's my base, times f of x plus change in x minus f of x. That's the height over x. Right, good. Well, so this is equal to the limit. We can cancel out that change in x again. The absolute value of f of x plus change in x of x. Now, I said something earlier about assumptions on f. What was it? Something about continuity. And that's going to bring us home, right? This function is continuous. So change in x going to 0 means this is approaching f of x, and by continuity, this will be equal to 0. And we've squeezed it between 0 and 0 now. So this term goes to 0, and this is just f of x. I could write QED here, but feel maybe a little disingenuous. I did a little bit of this, but it's pretty solid, right? So we got an intuition for this theorem, for this pretty fast. And by just looking at the geometry a little bit, we got there, right? First fundamental theorem, kind of done. We feeling good? So, kind of fun. Nothing revolutionary here. Now we're going to go on to the second fundamental theorem. But before we do that, I'm going to take us back. Remember what I said about the definite integral at the beginning? It is just area under the curve, right? So what the second fundamental theorem is telling us the easiest way to find the area under the curve. So I'm going to take us back to kind of the first people to tackle this question, which you may find completely unsurprising, was the Greeks. But then you think, wait, Jared, Greeks, area under curves, like polygons, pentagons probably, triangles definitely, but curves, like, dude, these guys didn't even do algebra. It's like they didn't even have x until Diophantus, and that's 500 years after the example you're about to give. And you'd be completely right. Which is going to make the following all that more incredible. And why is that? So the story normally goes like this. I'll just interject a little math history. In the 6th century BC, the Pythagoreans sought to base everything in arithmetic, in number, their math, their music, their astronomy. And this was going fine until they discovered something that they did not like. Something very upsetting. And does anybody know what that was? Where it's irrational. Yes, irrational numbers, right? In particular, they would have known that square root of 2 was irrational. Namely, it can't be written as a over b, where a and b are integers. And they did not like this at all. Right? Even just thousands of years later, this in the 19th century, Chronicle very famously said, the integers were made by God, everything else is the work of man. So to the Greeks, right, this is some devilry and not a good basis for doing all of mathematics. So they pivot, they say, instead, we're going to base all our mathematics on geometry, where we can safely instantiate any number concretely as the length of a line segment. Like this will be a better basis to geometry, and they felt more ontologically safe doing mathematics this way. Fast forward 300 years to Archimedes. He wants to tackle area under the curve with one proverbial hand tied behind his back, right? At this point, they have an extremely robust and successful geometry, but they have utterly no algebra. And right, it's a lot of it that we've been doing, right? So how is this going to work? Well, it uses something called the method of exhaustion. And if you ask the right calc student of mine, they will tell you the method of exhaustion is how I do everything in my calculus class. To the Greeks, this meant something very particular. And specifically, if they wanted to find the area of something, that wasn't a polygon, they would do something like this. They would inscribe polygons inside the shape, and that were more and more better approximations of the shape, or simply add more and more polygons inside the space that's left over, kind of tessellating it, so that, and polygons are easy, they could find the areas of these, right? So if they had some kind of sequence of polygons that filled up the space, they knew that the area of those polygons converged to the area of the shape, which is truly incredible, right? They have a pretty well-formed idea of a limit 2,000 years before Newton and Leibniz formalize kind of the idea of limit, and that's even 200 years before limit is made rigorous in the 19th century, and we're still in BC here. But of course, they were kind of dubious about this. Think like Zeno's paradox, right? But the thought was there. They just didn't quite have the tools that we have. So how would this work? My favorite example is the circle, right? You want to find the area of a circle, right? Very infinite shape, very smooth, right? So you could start by inscribing a triangle, right? Terrible. Terrible approximation. Okay. I don't want this to start to look like satanic or anything, but well, it is a rectangle. Squares, regular polygons. Better, right? We could do a hexagon. Gosh, that is not regular. That is an octagon. We could do an octagon. Much better. We could do like a trilagon, a 1,000-sided polygon. This is Kant's favorite, And at that point, it's a facsimile of a circle. You can see how the area of these shapes should converge to the area of a circle, right? So they knew about this, right? But they didn't have the tools that we have, because you could very easily show that the area of a regular n-gon, n times sine of pi over n times cosine of pi over n. In particular, a regular n-gon where the distance from the center to any of the corners is 1. That's the area. So in our modern parlance, we would say the limit as n goes to infinity of this, right? And by our geometric analogy, we know that the areas of polygons these converge to the area of a circle of radius 1, which is pi. Okay, so we can do this now. So if you want, at home or out there, take your favorite big number, maybe 1,000. You might not think that's very big, but and do 1,000 times sine of pi over 1,000 times cosine of pi over 1,000. You should get a decent approximation of pi. So a nice little tool here in a pinch, right? If you need a good approximation for pi and you already know it to infinitely many degrees of accuracy, you could get some digits of it. Yeah.
What would you do if you didn't have pi?
Let's not worry about that.
Okay.
Right, probably not this. Maybe instead you sum up the first 100 reciprocals of squares, and then you multiply that by 6 and take the square root. You could approximate pi that way.
Or you can live in Indiana.
Oh, true, but that's for another time. Legislature. So, right, this is the method of exhaustion, right? So let's fast forward to what's his name? Archimedes, right? 3rd century BC. He's going to take on area in his quadrature of the parabola. So, an empty space. What does that mean? Consider the following. Right? We have a parabola and we have a line. His goal was to, for any parabola and line, find this area trapped between the shape, right? And this may seem weak, but one thing, like this is actually strictly stronger than just finding the area under a parabola, because we could take the x-axis as our horizontal line. So it's stronger than that. And now today, how would we find this area? We would, this is some quadratic polynomial. We would find out what the function is. This is a line, and we just integrate their difference, right, from here to here. That gives us the area, right? Calc 1 or Calc 2, whatever that Calc 2 first week. Here's the problem, though, right? No algebra. What? So to him, what would a parabola have been? Would have been a conic section, right? In particular, it would have been the intersection of a specific plane with a cone. And it turns out you can construct any quadratic parabola, any quadratic polynomial that way. So pretty ambitious. He wants for any line, for any parabola, to be able to find this area, only using geometry, right? So where do we start? Well, maybe unsurprisingly, we're going to start with a triangle. So what are our vertices? That seems like a good candidate. That seems like a good candidate. And what about our last vertex? Seems kind of arbitrary, right? Can anybody think of a point along this curve that is less arbitrary?
Straight across.
I think you guys are saying the same thing, right? You have the maximum. Oh, well, which has the horizontal tangent, so I don't know if that's what you meant. That's not the one I'm thinking of. What do you mean by straight across?
Take the horizontal line to the intersection. And where it
Ah.
intersects with
So that's another one. We have a candidate here at the maximum. We have a candidate here. But neither of those.
Where the parabola has the same slope.
I love it. This is what he does. He picks the point where the tangent line is parallel. Tangent line to this curve is parallel to the line. Kind of cool, right? Why? Well, okay, we'll see.
Did you get this Archimedes?
Mm-hmm.
Yeah, and also how?
How?
Yeah.
We're not gonna worry about that.
Facts are constructible numbers.
Well, I mean, they could understand this. Like they could. Would he be able to find this point? Not necessarily.
Right.
But what he does is strong enough to conclude a lot about this area.
Okay.
Right. He doesn't need to actually like locate this point. They don't. I mean, of course, they don't even have a Cartesian plane. They don't have anything of it. But understanding this relationship is enough to find this area of this triangle, which turns out to be what he needs to. So I'm going to call the area of this initial triangle A1, and I'm going to call the area of the whole thing A. That's our goal, right? So we have A1. That's a start. What now?
What process on the other two?
Yeah, we have same thing now. A parabolic segment and a line and another one here. So do it again. I'm not going to draw all the tangent lines. It's going to get really gross. A2, A2. And here's the part that I'm not going to explain because there's no time. A2, he was able to show was 1/8 A1. We have two of them, right? That's all right. Do it again, right? We have 4 now. A3, A3. A3. This is degenerating. You get the idea. A3, right? A3 we showed was 1/8. By the same argumentation was 1/8 A2, 1/8 squared A1. And how many copies do we have? Well, 4. 2 squared. So squared A3 equals, well,
It's still.
1/4 squared A1, right? Because 2 squared times 1/8 squared, bring the 2 in, becomes 1/4 squared, right? So what's happening here? Well, every step I take, I multiply by 2, the number that I have, and each area I multiply by 1/8. So I'm really multiplying by 1/4 each step, right? So I have A1 plus 1/4 A1 contributed by A2s plus 1/4 squared A1 contributed by A3s. And of course, this process goes on indefinitely, and I get this infinite sum, right? And I can factor out A, and I can write this in our modern sum notation. There's a 1 here, right, guys, when I factor it out, so this becomes, and what kind of sum is this? Everybody all together. Geometric, right? We can do this. We have the power of modern math. It becomes 1 over y minus 4 thirds. I gotta do myself. So A1, this becomes 1 over 3/4 or 4/3, right? I want to rewrite it like this though, because I think it looks better. Nice. Only problem is, of course, you can't do this, right? This is 300 BC. No infinite sums. Not a lot of arithmetic anyway. Just geometry, right? So he gets to this point. He's able to realize it's this infinite sum of this form. So to him, he just sees this. And he's like, all right, I'm screwed, right? That's it. And we go home. But we gave it our the best try. No. This is incredible. If you don't think that this is cool, then you don't like math. I'll go home. Check this out. You don't do algebra, you've never done algebra in your life, and you gotta solve this infinite sum. He's like, I only know geometry. Start with a square of radius 1. Radius, sorry. Of side. Can't get any simpler than that, right? Break this into 4 boxes of equal size. So that's length 1/2, that's length 1/2, 1/4. We do it again. And now this is 1/4, 1/4, 4, 1/4 squared. Okay. Something's happening here. Well, I'm going to multiply by 1/2 and 1/2 again to get 1/4 cubed. 1/4 fifth. Great, we have a lot of boxes. Great. Well, notice these highlighted boxes are exactly this part of the sum, right? Without the 1. Right? So the sum of those areas should be this sum, right? And notice that every single one of these, we have 3 copies. 3 copies of this one, 3 copies of this one, 3 copies of this one. So 3 times 1/4 plus 1/4 squared plus equals 1. Right? So I summed up all the boxes, I should get the same area as the whole thing. They could divide, you know, they do some stuff. And now we add our 1 back in. And there you go. So he does this, and he concludes that the area under here is 4/3 the area of this first triangle, which he can calculate, of course, and we're done. And now for any of these shapes, all he has to do is find the area of this triangle, multiply it by 4/3, and he's good. Pretty incredible, I think. So this is 2,000 years before Newton and Leibniz are born. But now we're back to the present. You're in your first calculus class, and you're learning about the definite integral. How is it taught to you? Area under the curve, a priori. We don't know anything. What's our strategy?
Riemann sums.
Riemann sums, yes, right? Yes, right. I don't know how to find that area. You know what I know how to find the area of? Rectangles.
Translates.
I don't like triangles,
Me too.
but a little bit different. Alright, these are gonna look a little irregular. Alright, for those of us who have never done this, integral from A to B of f of x dx. We don't know anything else. This is the best we could probably do is say, take a bunch of things we know how to take the area of and get an approximation. This one looks like it's gonna be decent. But guess what? If we add more thinner rectangles, we'll probably get a better approximation, right? If I had 1,000,000 rectangles, all the errors would be so tiny, they would sum up to something still tiny. Trust me that the dimensions work. Right? So how do we write this? Write this as the limit of a Riemann sum. Right? And thank goodness for the second fundamental theorem that we don't have to do all integrals like this. What am I saying here? What I'm saying is take the area of all these rectangles and sum them up, right? F of xi is my height. Change in x is my width of each rectangle at the bottom, right? And this is going to be important. Change in x is just the width of them, so it's the length of my interval divided by the number of rectangles. They all have the same width. We might say the length divided by n. So the idea is, as limit as n goes to infinity, so the limit as the number of rectangles goes to infinity, this should get arbitrarily good, and we should get the area, right? And this is not super nice algebraically, but you can do it for simple functions. What does this look like, right? What method does this look like? Well, it's just the method of exhaustion with our new fancy symbols, right? We took a bunch of sigma is polygons. Hey, we took a bunch of polygons and added them up, and we did it better, better, better. And that's all it was, right? Nothing special here. But I still don't see the connection with the antiderivative. I see myself summing a bunch of rectangles up over an integral. What in the world does this have to do with the antiderivative, right? This is our big question. Here we go. Well, we're gonna have to take one more little foray into maybe surprising, almost pseudo applied topic, but not really. Linearization. What's linearization about? Okay, I have a function. Hopefully it's smooth. Maybe it's exponential, like this, right? And I have also the derivative of that function at this point. So I can define the tangent line. Something like that. Here's the idea with linearization. Lines are nice. Other functions are not nice. So this function, really close to x, should be really close to f of x. So instead of plugging into the white function, which might be gross, I'll plug it into the red function. It'll be easy, and it'll be a decent approximation when we're really close, right? This error between these functions should go to 0 as I approach x, right? For now, we have this gargantuan change of x, just to make things a little bit easier to write, right? So that error goes away. In other words, as change in x goes to 0, these two quantities should converge to one another. They both go to 0, but we're going to make use of this fact, right? So this first one is just the change in the function on the interval. Boom, boom. So that's just f of x plus change in x minus f of x. Whereas this smaller one, maybe less obvious, it's the change of the line. The slope of the line by design is f prime of x. This is rise over run. So I multiply by change in x, I should get change in y, which is this thing. Maybe, our spidey senses are starting to tingle a little. So as I said, the limit as change in x goes to 0. I haven't left myself over. Well, maybe I'll just write it this way. So what we've just argued for is the fact that f prime of x times change in x is approximately equal to f of x plus change in x minus f of x as change in x goes to 0, right? That's what we've been arguing for, that this line goes to 0 as change in x goes to 0. I can kind of see that happening. Look at this, right? F prime of x change in x. We're so very close to that right here. We're not quite there, right? But don't worry about this now. Sub functions, right? This is an arbitrary function. And how is it related to this function? Well, this is its derivative. This is its antiderivative. So I'm not gonna worry about that. I'll just rewrite this as some function. I don't need to know that it is derivative. Change of x is approximately its antiderivative minus derivative of x. Right? When change of x is going to 0. And here's where I'll get a tiny bit hand wavy, but we don't have really time to go through this all. I want to change this limit to the limit as the change of this isn't the hand wavy part. This is. Notice that n going to infinity, these are fixed, is equivalent to change in x going to 0. Okay. So instead of thinking about it as n goes to infinity, this is the limit as change in x goes to 0. And because change in x is going to 0, we have to you have to trust me that these errors are going to go away. Instead of fxi, change in xi, I'm going to put this. Antiderivative xi plus change in x minus antiderivative of xi. So what happens? Well, we showed that in the limit, this, the differential, is very close to this. It's related to the antiderivative. So instead of thinking about adding up areas under the curve, what I'm really doing is adding up how much the antiderivative changed on each interval. So I add up how much it changed from here and here and here and here and here. And now because we're adding up change, right? I just say how much it changed from here to here and here to here. I'm really just saying how much did it change on the whole interval. So when I sum up how much it changed on each of these subintervals, I just get how much it changed the whole interval. Well, that's just we ended with. That's what we started with. And even better, if you don't trust that heuristic, this telescopes. Isn't that nice? Notice that this term will be this term in the next sum. They'll cancel, and they'll cancel. So at the end, we'll be left with just, minus f of a and f of b. So if you know what telescoping means, like you can see it that way too. You get all this cancellation in the middle and just left with these two. And that's why everything boils down to just these two endpoints. I have absolutely no idea if this is like must be something similar, how this was inspired. I just kind of messed around with stuff. but I never thought it would leave me here thinking about this, thinking about, and it gave me a lot more intuition about like differentials and a lot of different things, right? But the kind of mystery of where the antiderivative comes from, it is here, right? It's from this idea from linearization, right? I needed to work backwards from the derivative to a function whose derivative is my original. And so that's not completely intuitive still, right? Like, but that's fine, because the mystery of mathematics is half of the fun. So I'm gonna move on and wrap up here. We feeling good about this? Do I want to? So let's see this in action real quick. Trying to decide if we should go like 10 more minutes or like 3 more minutes. All right,
Spirit motion.
I'm gonna do it. I'm gonna do the whole thing. So the other question I want to answer, which is much easier to answer, is how are these related to one another? Right? Why is one the first, one's the second? I think we kind of figured out why that one's the first. And I wanted to just use them to prove one another because I thought, especially using 1 to prove 2 was kind of funny, and I feel like everyone should know how to do this. So I'm going to assume this theorem and try to prove this theorem. So I want to find the integral from a to b of f of x dx. So what am I going to do? I'm going to do something that seems really wacky, and I'm just going to define an accumulation function on this function. Then I'm going to take its derivative, right? I got an accumulation function, I got this theorem. Obviously, that's what I want to do. A prime of x. I feel like Dr. McIntyre, he's one of my undergrad professors. When he got excited, he would go like this. Right? And now, of course, by the first fundamental theorem, this is just f of x.
That's for a transform.
And now I'm going to do something that seems really dubious. I just took the derivative. Now I'm going to take the integral. The integral of this is a of x plus some constant. I'm going to drop that for now because it's going to go over here. Definite integral of this. Antiderivative of x plus c. What have I done? Feels like nothing, right? But no, I've done something. A of a. I have 2 ways of writing a of x now. I have this way and I have the original way. I'm gonna use them both. The original way, integral from a to a, f of t dt. Well, what's the area from a to a? It's a line, it's 0, right? However, this is also equal to capital F of a plus c. Really feels like we're cheating here, right? So f of a plus c is 0. So f of a equals minus c. How would I do it like that? I don't know. C is minus f of a. We're almost home. A of b, we're going to do the same kind of trick, is the integral from a to b of f of b dt. Notice f of x, dummy variable, doesn't matter. Actually, I will. Now that there's no abuse of notation, I'll do f of x dx, right? From this. But it's also from the one on the bottom, f of b plus c. Well, plus c is minus a. And there you go. So it seems ridiculous, right? We just divide a function, we took its derivative, then we took its integral. Right? Kind of funny. But like if all you have is this, you could get here pretty quickly. And the other way, even easier. Far, I would venture to say, far easier. However, I tell my students this, I say, here's how you prove this one, extra credit, prove the other direction, I'll give you half of it, and none of them do it. But here we go. Well, we're going to start with the derivative of b straight up. Now, do we have the imagination to take the next step? Well, my second fundamental theorem. No, you got no other versions of SFT. This is just the antiderivative of x minus the antiderivative of a. We can, thankfully, the differential operator is linear, so I can just do these separately. F of x. That's a constant, so I take its derivative, I get 0. But guess what? This is the antiderivative of that. If that's just x. I have faith in them. I have more faith in them than they, right? See, I think I gave them like continuity and this. It's fine. Right, so that's how you would prove them from each other.
Strong finite type. Or shift finite type, you do, right? They're forgotten.
The slow Fourier transform.
So I want to conclude by saying one of these theorems in action, right? Because at the end of the day, this is actually magical. I have a curve. And I'm gonna find that area, and oh my goodness. I have a curve, and I'm gonna find the area. And it's gonna be somewhat symmetric. Right. That's fun. Not a hard integral. So I want to find this area. So what do? Integral from -1 to 1 of my function. Negative x squared plus by the second fundamental theorem. I take the antiderivative, becomes minus x cubed over 3. If you don't know why, don't worry about it. And I evaluate that from -1 to 1. This just means this, right? So first I plug in 1, I get -1/3 plus 1 minus the thing everyone forgets, right? The parentheses, I now plug in -1, this becomes 1/3 minus 1. Negative, this becomes positive, I get 2 minus 2/3 equals 4/3, which is exactly, perfectly the area under this curve. And I could have done cosine, I could have done any function, a lot of functions very easily where the areas would be more exotic, but I thought this was nice because, right? So it's familiar. Hopefully, we know that that tangent line is parallel to this line, right? This triangle has height 1, it has width 2. So this area is of course 1/2 base times height or 1. And there you go. Archimedes was right, and 2,500 years later, we have a very different way of doing it, which is still pretty beautiful, I think. Yeah, that's the stuff that I learned about the fundamental theorems of calculus over the last couple months, and I really appreciate you all listening. Thanks for coming.
Any questions?
When you were talking about how Archimedes did the triangle thing, you said that he took a step where he found out that A2 is 1/8 of A1. What is involved there?
That's so funny because literally ask me any other question. I don't think I have time to really go through that right now, and I think I would mess it up. So maybe we'll have to talk about it another time. I really should have anticipated that question though better. No, I don't think I have a good way. It's the same way of explaining it. Hopefully somebody has another question, because I really would.
I have a historical question, actually, I don't know. So when did the formula for, say, the volume of the cone, volume of the sphere, who came up with that originally?
I'm quite confident that the Greeks knew the volume of a cone.
See, I thought at least that, so do you know how they did that? Was it some kind of exhaustion again?
Oh, I don't think so, right, obviously they couldn't integrate a circle, I think I did come across this, like, I know that they knew how to do it, but I don't think it was the
I
same kind
remember
of
when I
method.
first saw that formula, and I think I heard the Greeks did it, right, and. I was like, exactly 1/3, and I pictured a bunch of guys wearing togas pouring sand everywhere. But, you know, they must have done something more sophisticated than that, maybe.
Yeah, so like for us, obviously, we wanna do that, we like do a surface rotation or
Right.
a volume of rotation. I'm trying to think how they would. I do think they do it, but I don't know how they did
They
it,
could
I don't think it was
approximate
methods
by
of
little discs, I
cylinders.
guess, or something, right? I mean, they could try to exhaust it that way.
I mean, of course, you hypothetically could do a three-dimensional version of exhaustion, but I don't know off the top of my head. But yes, they knew some of those areas. They didn't know the what's it called? The circumference of a parabola, because we still don't know that, which I think is one of the most insane things. But I don't know how they would have done it for three-dimensional. A lot of this was very much just me doing stuff and some of my relevant knowledge of history. So I probably should read a little more deeply into some of it. But yeah. Anything else? Yeah,
Would you be able to like email out a solution when you get it written?
yeah.
Okay.
If you look up quadrature of the parabola, you should be able to find things that step through it perfectly. But I really just didn't look very closely because I thought I probably wouldn't have time to go through that part of it, so.
Another question? I like that question. I think that's the first question in the history of the math club, where the speaker has been asked to email more math after the math club. So that's kind of cool. Okay, let's say Jared.
So Jared, suppose you have a smooth orientable manifold and you want to integrate the.
No. No man.
Oh, I guess I should have.
I really should have known someone was gonna ask that, and I thought about it, and I was like, I should know how to do this.
Okay, bye, everybody out there in the real world. Or, well, real